Hello to my wonderful students. Dr. Mandis here, talking today about nuclear stability, and that'll lead us into a conversation about half-lives. Typically, most of the chemistry that we learn, like we talk about in general chemistry, revolves around electrons, the movement of electrons in the electron clouds to make bonds, break bonds, make cations, anions, stuff like that. Nuclear stability, now we're venturing down into the nucleus. What's in the nucleus? Neutrons and protons. Just, you got the nucleus, you got N's and P's. That's it, right? Neutrons and protons that are in there. Therefore, the stability of the nucleus is going to be dependent upon neutrons and protons. There's a couple of different forces in there, the binding forces that hold them all together. And depending upon what's going on in there, if there's a lot of neutrons, if there's a lot of mass, then you can hold more neutrons to protons. If there's less mass, then neutron to proton ratio is like 1 to 1. What I have here is a graphic. And basically that graph shows little dots in this zone of stability here in this region, all the little dots for all known isotopes, okay, of atoms. It doesn't say the way you know what atom it is by the number of protons. Remember, the atomic number tells you what atom's what. If you look at it, at the very beginning of this graph, you have a line that's about 1 to 1. As the atoms get a little bit bigger, more neutrons can fit. And since this is the number of neutrons, you get a slope now that's greater than 1 to 1, so the curve starts bending upwards. So yeah, you just learn empirically that, hey, a larger atom can contain more neutrons than protons. Smaller atoms down at the beginning, not so much. As you read this graph, what this graph is showing you, you're supposed to be able to pick up that, hey, down here it's 1 to 1. Up here, it's about 1.25 to 1, 1.4 to 1, and then 1.5 to 1 up in yay. Okay, this is the line that it would be on if it was always 1 to 1, and clearly it's not always 1 to 1. So let's look at a couple examples of this and just sort of see what it means. First question right here. Which isotope is likely to be radioactive? I gave you all the same isotope. They're all isotopes of carbon here. Okay, carbon 12, 13, and 14. You're looking at the N to P ratio. The number one wrong answer that students do who aren't really paying attention is they give me 12 to 6, 13 to 6, 14 to 6, and I know that, hey, you're not focusing on the relative ratios of what is in the nucleus. It's the ratio of neutrons to protons. Why neutrons on top? Because you're always trying to deal with numbers bigger than 1 because they're nicer to deal with. All right. If you look at carbon, getting back to our conversation, we're looking at carbon. Carbon's way down here on the line. So we're looking for a ratio of 1 to 1. In our ratios, all right, the one that's furthest off the line, the one furthest from 1, happens to be carbon 14 with its 8 to 6 ratio. So carbon 14 would most likely be radioactive. Remember, we're looking for the one that comes off the line. He could be too high or too low. Doesn't really matter. Just the one furthest from the zone, this whole zone of stability. Let's do another one that's a little bit bigger. Okay? Don't want to scroll too much because I kind of want to keep it there. Alrighty? What we're looking at is this example here. We have 3 isotopes, yttrium, zirconium, niobium. Alrighty? They are looking like we're at atomic numbers 39, 40, and 41. Let me grab the red pen. Oh, green pen will show up better. 39, 40, 41. We're about up in here of the zone of stability, and that means we're looking for about a 1.25 to 1 ratio. Well, let's see what ratios we got. Calculate the ratios using the numbers, but remember we need neutrons. The atomic mass is neutrons plus protons, so you got to subtract. 85 minus 39, we get the neutrons, we get 46. Then we do 90 minus 40, get 50. 93 minus 41, we get 52. Dividing by the atomic number on the bottom. We need to simplify it so we can actually compare to this 1.25 to 1 ratio. And when we simplify, you get 1.18 to 1, 1.25 to 1. That looks like the most stable because it is the ratio. 1.27 to 1. The winner here, the one that's most likely to be radioactive, is the one furthest from 1.25 to 1. And in that case, that would be this guy. He's 0.07 away. He's 0.02. So this guy is the yttrium. Okay, so it looks like the yttrium-85 isotope is most likely radioactive. If you're in my class and you want to answer it, you need to say all this good stuff. If they're radioactive, then they're going through a transformation. They're losing radiation. Radiation can be in the form of mass, energy, or both. All right. Radiation is a first order kinetics gig. First order kinetics, if you recall, has a half-life. Where is that? I know it's right down here. A half-life that doesn't have any concentration terms. First order kinetics is not based on concentration, therefore it won't change as the concentration changes. So for radioactive decay, it's a constant. So take a peek at the one example I got here for you. P32 has a half-life of 14 days. What exactly does that mean? Number one, wrong answer is people say, hey, after 14 days, half of it's gone. Well, what is it? After 14 days, indeed, half of it is gone. Half of the P32 is gone, but it's now sulfur 32. You still have 50 grams of material. 25 grams will be P32, 25 grams will be S32. After another 14 days, it's going to decay again. Half of the 25, not another half of the 50, half of the 25. We got 25 grams of P32, it's going to be 12 and a half. The way I got this is I did 25 plus the 12 and a half. Alrighty? Radioactive decay is first order, as I mentioned. First order kinetics means it's this equation. So if you want to figure out time or how much remains of something, how much remains is here at A. The original amount would be A naught. The time is T. We don't really want to factor in the number of half-lives, so we're going to substitute in this half-life equation in here and rearrange. Let me blow this up a little bit. Rearrange and get the whole enchilada right there. Natural log A is negative 0.693. The half-life times the time that you're talking about times the natural log of the original amount. Alrighty, looking at an example, right? That example, we go back to P32 with its 14-day half-life. After 10 days, how much is gone? For even number of half-lives is easy, just divide by 2. What if it's not even number? You need to follow back on the equation, the first order integrated rate law. Alrighty? If we do that equation, substitute in our values, half-life is 14 days, okay? The 50 grams would be the original amount. Our 10 days is the amount of time that we're talking about. Simplifying that side, we get natural log A, 3.42. How do you undo a natural log? Natural logs are base E. Raise both sides to the power of E. That will cancel out the natural log. And so the amount that remains would be 30.6 grams of P32. So it's not so bad. Plug and chug, and we'll roll with it. Hope you learned something. Hope you like it. I'm Dr. Mandis. Talk to you later. Take care.